This is the last lecture on carbocations. So just a quick review. Last lecture or presentation, we looked at the generation of carbocations. And as we pointed out, they are typically made by the heterolytic cleavage of a carbon X bond, where X is a good leaving group. Next, we looked at the rearrangement of carbocations. The driving force here for the rearrangement is the stability that's gained from a tertiary compared to a secondary or a methyl. So that's typically we'll see bond migration or even hydride migration to form a more stable carbocation. In this presentation, we will look at reactions of carbocations once they are made, and if rearrangement is possible, what are possible products. Okay, let's start. First, since carbocations are sp2 and flat, so here's our carbon. It's sp2 hybridized orbitals, so here's 1, 2, and 3 sp2 hybridized orbitals. And we have here a vacant p orbital that's unhybridized. Notice again, it's vacant, so that's why it's a carbocation which is positively charged. Since it is flat, the reaction with a nucleophile, notice again, a nucleophile has at least one unshared pair of electrons. Of course, electrons will react with positive or carbocation. So this nucleophile here can add to either side of the carbocation to the p orbital. And notice again that there's a 50-50 probability or possibility of adding from either side. So if the carbocation generated from the initial reaction, in this case it's a addition reaction, so we have HCl adding to this to generate the carbocation right here. If when the Cl adds, it can add to either side to generate 50% of one enantiomer and 50% of the other enantiomer, a racemic mixture. Let's look at another type reaction. So here, this is not an addition reaction to create a carbocation, but this one is a substitution reaction. Notice it's a SN1 because SN1 reactions generate carbocations in the rate determining step. So here is a good leaving group, bromine. It will leave in the rate determining step to form a carbocation. In this case, a secondary carbocation. Why secondary? Because there are 2 alkyl groups that's bonded to that carbon, making it a secondary. In the presence of a nucleophile, such as water, attack can occur from the top side or the opposite side to generate here an alcohol, one enantiomer, and the other enantiomer in equal mixture. Notice again, if it's equal mixture, and that's why the term racemic comes about, because of equal mixture. I should point out again that this type reaction is called solvolysis because the solvent here is also the nucleophile, water, as you can imagine. Let's look at another type example, another example here of SN1 that creates a carbocation intermediate. That's sp2, trigonoplanar, and flat. So as you can imagine, this is chiral, but in the rate determining step where this leaves, it generates a flat carbocation. This is our solvent and also our nucleophile. So these reactions SN1 are typically described as solvolysis because the solvent is also the nucleophile. So you can imagine this nucleophile attacks the flat sp2 carbocation that's generated from the leaving of that good bromine to give racemic products here, in which the nucleophile are shown here from the solvent. Just another example, stereogenic. This is written in the Fischer projection. You may recall the Fischer projection from our earlier lecture, whereas this one is called the dashed wedged representation. So with this Fischer projection here, this bromine leaves, even though it's chiral, but it leaves to form a flat carbocation. The solvent here, which is also the nucleophile, attacks the flat carbocation from either side to generate a racemic mixture. Notice again racemic because we have a chiral carbon here and a chiral carbon here, and they are of opposite configuration. One is an R and one is an S. Let us look at a unique reaction here. So here we have a reaction. Here's our leaving group. Here we have the phenyl bonded to the adjacent carbon, and in a reaction with acetic acid or the acetate anion, we get this as a product. Notice again that this is retention because this OAC comes in from this side, so the stereochemistry remains right here compared to here. So the same side that the OTS or the tosylate group leaves from, the acetate comes in. The other product that's generated is, notice there's a migration of the phenyl from this carbon over to this carbon to give this product here. So there are two products that are generated. The key here, or the key observation, is that after this leaves, this type product here, A, is not a racemic product, or there's no racemization about this carbon, but retention. Let's see if we can explain that. We can explain that because if this leaves to generate the carbocation, there's a migration here. In fact, the migration occurs while this leaves, while the positive charge here is being developed while the OTS leaves. Once the migration occurs, we have a transition state that looks like this, or an intermediate, should I say, that looks like this. And notice one side is blocked by the phenyl group. So the bottom side here, as drawn, is blocked. So therefore the attack of the nucleophile must come from the opposite side, from the top side, so to speak, because of the phenyl group blocking the other side. So in terms of product A, you will see here that it attacks right here to give product A retention, because OAC comes in from the same side that the OTS or the tosyl group leaves. When migration occurs, B, OAC attacks this carbon here, as you can see here, to give this product where the phenyl group migrates. Of course, as we have said in the last lecture, the phenyl group has a great tendency, one of the greatest tendencies, to migrate. So therefore it comes in again from the opposite side, again because this side is blocked. So this explains the formation of two different products. In this course, you'll get questions where you're asked to explain the formation of different products using the concepts that we have explained throughout the course of this lecture or of this course. Let's look at another situation here, another reaction. So for the reactions shown below, the following observations were made. A, the first reaction here is faster, 100 times faster than the second one. How do we explain that? Another observation is that the first reaction proceeds with retention of configuration. So let's see if we can summarize that observation. So for this reaction here, it's faster than this. The only difference between this reaction and this reaction is this double bond right here. This double bond is here and there is none here. So that's the only, the only difference between the reactants. The other observation is the first proceeds with retention. So in other words, here the nucleophile comes in from the same side that this leaves. The nucleophile comes in from that same side to give the retention product. Notice there's no product where this comes in from the opposite side, the axial side. So it comes in from the equatorial side and not the axial side as shown here, as is possible here. For the second reaction, what we have here, it's slower, no double bond, so that obviously plays a role. Also, when this leaves, the acetate nucleophile comes in from the equatorial side to get this product, and also from the axial side to get this product. So in other words, we have racemization at that carbon. The question is, how do we explain these observations? Let's see if we can in the next slide. So the double bond that's here, it's possible to interact with the carbocation that's developed after the group has left. In fact, this double bond assists in the group leaving to form the carbocation. So we call that Anchomeric assistance. So this type carbocation, as we have seen from earlier lectures, is the homoallelic carbocation. Let me emphasize again. So these electrons here assist in the group leaving to form the carbocation. This is a stable carbocation because of the electrons interacting with the p orbital. That type of assistance is called neighboring group participation, neighboring group participation, or Anchomeric effect or assistance. So the bottom line is that these electrons assist in the leaving group leaving to form this type carbocation that's very stable, the homoallelic carbocation. Another representation of the homoallelic carbocation is shown here. So this positive charge is really delocalized right across these atoms here. As you can see, this side here, the axial side, is blocked because of this. So attack must occur from the equatorial side to give that only product shown. So that explains that type reaction. Let us look at another observation here. Here we have three molecules. They all have good leaving groups, tosylate, but the tosyl leaving group, and will react by an SN1 reaction in a solvent such as acetic acid by SN1. So what is observed here really is that the first molecule here reacts much faster than the second molecule. Notice again, The only difference between this molecule and this molecule is that it has a double bond here and this one does not. So the question now becomes, why does this molecule react by SN1 mechanism much faster than the other one? The other observation is that there is a retention of configuration on the substitution. So once there's a substitution here, the nucleophile comes in from this side and not from this side. For this reaction here, the nucleophile comes in from this side and from that side. So once this group leaves to form the carbocation, which we'll see on the next slide, the nucleophile, which will be the acetate, or some nucleophile, can come from either side to give racemization. So the observation is that this molecule here reacts much faster by SN1 than this molecule. The only difference between these two molecules is that there's a double bond here and there's none here. Interestingly, this molecule here, which also has a double bond and the same tosyl leaving group, reacts ordinarily. So just as a typical SN1 reaction, not any faster, not any slower, typical racemization and no retention. Let's see if we can explain these observations. As you can imagine, it's a homoallelic conjugation. So homoconjugation here, double bond here will assist in the group leaving. In that case, it was the tosyl group leaving to form a stable homoallelic carbocation. So that's what's happening here. So here is an illustration of the electrons here, or the pi electrons here, interacting with the p orbital. The aspect here, why do they interact? Because of the geometry. This Norborneal system here has the perfect geometry for this p orbital to sit right in the middle of those p orbitals, so therefore there is an interaction. So it works only because of the geometry that's generated by this type Norborneal system. Here's another representation here. So this represents here the interaction, and of course there's a positive charge. So let's see if we can explain that a little further. So this leaves, but as it's leaving, these electrons here assist in its leaving. That's why it's called an Anchomeric assistance, or neighboring group participation, to generate here a stable or relatively stable carbocation. Homoconjugation. Here's another representation of this. Stable. Why I'm emphasizing stability is because, of course, you may recall from your Gen Chem or from your earlier lecture, if the transition state leading to a carbocation is stable, the reaction is faster. Just to illustrate here, we have electron reaction profile. If this leads to an intermediate here, here's our activation energy to generate this carbocation. If this carbocation is stable, this energy of activation is low compared to another intermediate that's not as stable. So therefore, as you can see, this energy of activation for the less stable carbocation is higher, faster rate, compared to the energy of activation for this more stable carbocation, faster rate. Let me say that again. So this is a less stable carbocation, slower reaction. I think I said the opposite earlier. So this reaction here to give a less stable carbocation has a higher activation energy, so therefore slow. This reaction profile that gives a stable intermediate has a lower activation energy and hence faster. Okay, so the bottom line is that this allelic or homoconjugation structure presents stability compared to the other, which is not stabilized by the double bond. So therefore this is stable, faster reaction compared to the other one that does not have a double bond here. In terms of the retention of configuration, as you can imagine, this side is blocked based on the orbitals, as we have seen on the previous slide. So the nucleophile comes in from the same side as the leaving group leaves, so we have retention of configuration as shown here. So here is the product with retention of configuration. So once again, just to summarize, the leaving group leaves, but these electrons here assist in its leaving to generate here a stable carbocation called a homoconjugation carbocation. It's also considered Anchomeric assistance or neighboring group participation because these electrons assist in that leaving to give this stable carbocation. Because it's stable, it is the energy of activation leading to this carbocation is small, fast reaction, because this is the rate determining step for the SN1 reaction. Once we have the carbocation, the stabilized carbocation, this side is blocked, one side is blocked where the double bond is, so the acetate comes in from the opposite side. By the way, this should be common C. Comes in from the opposite side to give retention as the product. So that explains it. So here is another example. Notice again, for this one, this product, this reactant here, gives retention and not racemization at this carbon. This reactant here gives racemization at this carbon. Let's see if we can see the only difference or the difference between these two reactant molecules, because everything else here is the same. The nucleophile and the nucleophile here is the same. The only difference here is that the tosyl group here is in the equatorial position and the tosyl group here is in the axial position. So obviously that makes the difference. Obviously that makes the difference because that's the only difference between these two reactant molecules. Let's see if we can use that observation to explain the difference in products that are formed. So, as we have seen before, we have seen the Norbonial cation or the non-classical cation. How does that work? We have the sigma bonds here. Notice it's the geometry of these sigma electrons are perfectly aligned to assist in this group leaving. Notice assist in it leaving. So we have Anchomeric assistance or neighboring group participation. Because of this assistance, we have here a stabilized Norbonial cation or non-classical cation. Stable, fast, to generate this stabilized carbocation. The nucleophile can come in from this to attack this carbon or this carbon here, not from the axial side. Notice if it comes in from this side, it gives a product, this one, and it comes in from this side, it gives this product. So you should really look at this carefully and see that attack here gives this, because you can turn it over, and this gives this one. So this attack here gives this carbon, and this gives this one. So you should rationalize that these two are the same. So again, it's blocked from coming in from this side based on the orbitals that are interacting here to stabilize that one. For this one, however, notice that the tosyl leaving group is here. So there is no Anchomeric assistance from neighboring sigma bonds as we have here. So therefore the carbocation that's generated here, the nucleophile can attack from the axial side, equatorial side, pardon me, or the axial side to give racemization at this carbon. So just to summarize before we leave this slide here, with the leaving group in the equatorial position, it's perfectly set up for the sigma electrons to give Anchomeric assistance as this leaves to generate the Norbonyl cation or the non-classical cation here. Stabilized compared to the cation that's generated here. Non-stabilized, so it's a non-classical cation here. This is stabilized, so therefore the energy of activation leading to this cation, or the rate determining step, is low, which means that it's fast compared to this one. And the nucleophile can attack from this side and not from this side, because it's blocked with that interaction to give retention of configuration, whereas this one will give racemization at that carbon. Okay, let's look at another type rearrangement before we leave. This is fairly simple compared to the ones that we've looked at before. If we have this, and this is described as our allelic chloride. Why allelic? Because here's a vinyl group, and this carbon here's the allelic carbon. So we have here allelic chloride. It's a leaving group, so as you can tell, it leaves to give an carbocation. But here is the expected product, because here's our nucleophile, and it comes back in here. But here's the unexpected, because it's bonded to this carbon compared to that carbon. So let's see how we can explain that. First, to explain the expected product, it leaves to give here a resonance stabilized carbocation called the allelic carbocation. It's resonance stabilized, so therefore the transition state is the energy of activation leading to the transition state here is low, which means that you'd expect this reaction to be much faster than if this group was not present. Okay, these are resonance stabilization to show that this carbocation here is stable. But to explain the expected product here, the nucleophile attacks this carbon here, as shown here, and of course loss of the proton to give the expected product. So the take-home lesson from this slide is that the leaving group leaves to give the resonance stabilized carbocation. Why am I emphasizing resonance stabilized? Because the energy of activation for this rate determining step is low, fast reaction because of the stability gained by resonance, compared to if this double bond were not present. And of course, in the fast step, here the nucleophile or the solvent, because it's solvolysis, attacks this carbon here to give this intermediate loss of proton here, give this product. So as you can expect, the other product here is HCl. To explain the unexpected product, same rate determining step to give our resonance stabilized carbocation. But as you can see here, there's a positive charge right here. So in other words, the positive charge is delocalized throughout these 3 carbons, which means that the nucleophile can attack this carbon just as well as this carbon. So here is that attack, an intermediate here. Loss of proton gives the unexpected product. So you should be able to explain the formation of expected and unexpected product based on the carbocation that's formed. Before we leave, let's look at a last concept here, where we have a lone pair of electrons assisting in the carbocation's formation. Of course, as you know, that's also known as Anchomeric assistance or neighboring group participation. So if we have a molecule like this, where this is our leaving group, and here's an atom someplace in the molecule that has a lone pair of electrons. Notice it has to have at least one lone pair of electrons. It can assist in forming the product. It can assist in forming the product or faster reaction. Let's see how that happens. So these electrons here can assist in this leaving by reacting with the carbon that has the leaving group. So in other words, these electrons here can come in to this carbon, assist in pushing out, so to speak, the leaving group. What's generated is an intermediate looking like this. Of course, the nucleophile comes in from this carbon and regenerates our X with the unshared pair of electrons, but this is the product that's shown here. But the key here is that these electrons assist in this leaving group leaving to form a carbocation or stabilized carbocation. And of course, since there is a pair of electrons assisting in that happening, it's called Anchomeric assistance or neighboring group participation. Here's an example. As we have seen, mustard gas is a deadly gas. It was used, I think, in World War I. So it's a deadly gas, World War II. It's a deadly gas, and it's owing its deadliness to the sulfur that's present here, which has 2 unshared pairs of electrons. It has but one can serve in Anchomeric assistance as this group leaves. So this sulfur here, this electron here, assists in this leaving to generate this type carbocation. So once this is formed, the deadliness of mustard gas comes about because this intermediate here interacts with the DNA of our body strands and leads to cell damage. So this assists in this formation, very reactive here with the DNA of the body because it has nucleophiles on the DNA, and of course it gives us that deadliness. But if there is water present or in another reaction medium, we have water as the nucleophile. As you can see here, the water comes in and generates here this as the product. So as you can expect, this reaction is very fast. It can happen again. So you can have here 2 OHs as the substitution product, but the main take-home lesson here is that there is a pair of electrons that assists in the group leaving, neighboring group participation, to give an intermediate like this, and this intermediate will react with nucleophiles such as water to give a product. But if it's in the body, it reacts with DNA to cause cell damage and death. So that caused by the nucleophilic, or the, should I say, the neighboring group participation of this. Notice this type compound here, 1,5-dichloropentane, does not have the same effect because there's no neighboring group participation in this molecule. In other words, there is no atom that has an unshared pair of electrons that can assist in the chloride leaving. So here we will just have a regular SN1 reaction, in fact a very slow one, because as you can imagine, it's a primary carbocation that's generated. And lastly, let's see if we can explain this. So explain the following observation. The rate of acidolysis. Acidolysis just means here the solvent is acetic acid, where the nucleophile is the acetate anion, where one of the molecules shown below is much faster than the other. So notice here, much faster. So as chemists and scientists, let's see if we can see the difference between these two molecules. Since the solvent here are the same, the leaving group here are the same, the only difference here is that this one has an oxygen and this one does not. Note again, the ring size here is the same. One observation here is that there is at least one unshared pair of electrons on this oxygen, and there is none heteroatom here. So as you can imagine, these electrons here can assist in that leaving. So we have Anchomeric assistance, which gives us a stabilized intermediate. The energy of activation leading to the intermediate from this reaction here is low, which means it's fast because it's stabilized. Intermediate is stabilized. So for the rate determining step, this is fast. This one, however, is not stabilized because it is just a leaving group generating a carbocation, secondary carbocation here, that's not as stabilized as this one here. So therefore, the energy of activation for the formation of this carbocation is higher, slower reaction. Notice greater activation energy, slow reaction, lower activation energy, fast reaction. So therefore, this reaction here is faster due to Anchomeric assistance or neighboring group participation compared to this one here that does not have neighboring group participation. I think this is the end of the lecture. Yes, it is. So this is the last lecture for carbocations. So continue reading up and refresh your memory on the different aspects of carbocations. I know a lot can happen for carbocations, rearrangements and different type reactions, different type stabilities, etc. So make sure you read up on this and understand the concepts so you can apply those concepts to explain different observations. Our next lecture will be on carboanions. That's the carbon with 2 electrons, or the carboanion. And I'll try to get that posted over the weekend. So continue studying hard.